Hello, welcome everyone to our weekly live stream on vector databases. My name's Neil Canungo. I'm your host, and today I'm joined by Megan McParland, who's doing her very first live stream. So if you can welcome Megan on. Megan, do you want to say hi to everyone?
Hi everyone.
Good to have you, Megan. Today I'm really excited because we're going to show something different than we've shown in the past. We're going to be showing the pattern similarity with vector databases example notebook, and we're going to go through that hands-on today. And I'm excited that we're going to be showing structured data search with vector databases. So in the past, we've shown images and music and documents, but what about if you have structured data, tabular data, or data that is in a time series orientation, and you want to start to find similarities or anomalies with that data? We're going to be able to dive into that today. So, without further ado, let's go ahead and get started. Before we get going, I wanted to let everyone know, just kind of my standard introduction, let you know that you can sign up for KDB AI and follow along with our example workbook today. You simply go to kdb.ai in your browser, go to sign up in the top right, you'll fill out the form, you'll get a confirmation email that you click. When you click that, it'll start your instance. And then you'll get another email that just tells you how to log in. It gives you a link at the top. That's cloud.kdb.ai. So you'll have your sign-in credentials, and then you'll be presented with the administration UI. And the administrator UI gives you an API endpoint that you can see in the center of the screen, and also gives you an API key. Remember to kind of copy that API key down for your records, so you can make sure you can access your instance. If you ever lose the API key, you can just delete the API key and create a new one if you need to. So we do know that vector databases are new, and we're going to do a little introduction to vector databases. But before that, I wanted to show you how you can get this notebook, this Jupyter notebook. So on kdb.ai, go to the Learning Hub at the top of the screen, and you go to Pattern Matching and Outliers. This will be in the samples of the Learning Hub. When you go there, you'll be presented with a screen that has a button to download on GitHub, and you can download this Jupyter notebook and follow along with us today. The vector database introduction, I'm going to kind of condense this down because we've done this introduction in past sessions, but I do know that there are some people that are new to vector databases, so I want to go over some of the key concepts and key aspects of vector databases. So we have a vector database application. You'll see that there is source data. It runs through an embedding model, often a deep learning model, that takes structured and unstructured data and condenses it down into a structured vector format, which is a series of numbers essentially. And those series of numbers for each of your data, that your input data that's coming in, gets stored into a vector database. That's KDB.ai in this case. And you're able to query that. You find similar vectors. One of the more powerful things about a vector database is that it allows approximate searches, so you don't have to have exact matches to pull results. You can find things that are related to each other, and using these embeddings, these vector embeddings, you're actually getting documents and time series data and other data that is related to each other through the magic of the embedding method. It's related to each other, but it's not, doesn't have to be an exact match again. So those query results are returned. You can do some post-processing, some re-ranking, some filtering, and that's fed back to the application where you are, and you can continue to do queries on your vector database that way. Vector embedding, just to go over what a vector is, you have here two-dimensional vectors and three-dimensional vectors. These are showing a mathematical representation of magnitude and direction is really what this is. And when you have a vector embedding, you might have hundreds or thousands of dimensions. So if you imagine expanding this on into more dimensions, there you go. There you have it. You have a vector embedding. There are different embedding models for different data types. So if you have audio, if you have text, you have video, you'll use different models, and you want to use, when you're querying, you want to use a similar embedding model that you used, or often the same embedding model that you use to generate the embeddings. So if we picture these embeddings in space, they might be these yellow dots. So those are all of the representations of our data. We do a query, and that query goes through the embedding model, creates a query vector, and that query vector lands in vector space. From that vector space, you can then get the nearest neighbors. You can use different similarity metrics like Euclidean distance, cosine similarity, or dot product are three that are used with KDB AI. So with that, we're going to move on to our hands-on tutorial. Thank you for sitting through my introduction, but let's get down to the fun stuff. We're going to be looking at machine data today, and we're going to be finding similar patterns. We're going to find where there's machine failures and find when other sensors have similar patterns as those machine failures. This type of application can be used in financial markets. It can be used with defect detection and manufacturing. It can be used with predictive maintenance. You name it, there's a lot that you can do with time series data. And this is just our introduction into time with vector databases. So with that, Megan, I'm going to hand it over to you. And you are now on screen. So whenever you're ready, feel free to start.
Perfect, thanks, Neil. So hi everyone, I'm Megan, and today I'll be demonstrating how to perform pattern matching on sensor data using KDB AI. So first, a bit about what pattern matching is and why is it useful. So today, many manufacturing organizations rely on sensor data from plant machinery to determine productivity and to prevent downtime. So a key aspect of this is temporal data, which enables engineers to determine point-in-time events that could indicate component failure. So in our example today, we will retrieve all historical time series that match a particular pattern, transform this data into embedded formats, and store them in our KDB AI database as vector embeddings. So let's get started with the example then. So before we start, there's just a few libraries that we need to import. The most important ones being matplotlib, which will help with visualization later on, and our KDB AI client, which allows us to speak to our KDB AI database. And here we're just defining some helper functions and setting some filters on warnings. So the dataset we'll be using today comes from Kaggle. It's a water pump sensor dataset. And here we're just going to download and extract it locally. So once you do that, you'll see that you have your sensor.csv file. We're going to read this in using read CSV, and then we're going to load this into our pandas data frame. So once your data frame has been loaded, then you'll be able to see that we have 52 sensor columns along the top, as well as our machine status column and our timestamp column along the left there. So these results come from 52 sensors on a water pump collected over a period of 6 months. For the purposes of this example, and for the simplicity of creating our embeddings, we're just going to be taking a look at our first sensor, the first sensor. So to get started, let's do some pre-processing. So here we're just going to be dropping any duplicates, removing any columns that are unnecessary, and converting our timestamp to a date time format. So once that data frame is loaded, then you'll be able to see our clean data frame ready for use. So as I mentioned before, we're only going to be looking at one sensor, and we're going to use that machine status column. We're going to take a look at it and see wherever it was marked broken. We're going to take a look at this and plot that using our matplotlib visualization, and we're going to take a look over the 6-month period to see where that sensor value, how that sensor value generally performed. So see here, we've marked in red axis where the machine status has been marked as broken. And you can see here it oscillates around the 2.5 mark, but there's also some huge drop-offs along the way. These also coincide with the machine status being broken. But this is the data we're going to use to create our embeddings and perform our pattern match. So when creating our vector embeddings, we're going to be using a combination of windowing and normalization. This is quite a simple approach, so there's no real need for complex modeling or domain-specific expertise, but you can replace this with any form of embedding technique you choose. So let's create our embeddings. We're going to start off by grouping the 6 months of data by a window size of 24. And we're also going to be adding a step size of 10, which means there's going to be an overlap for each window. So if we define that as windows and we take a look at the variable we just defined, you'll be able to see here that we have a list of 24 values starting from the very start, going all the way down to the 23rd index. Now it's also important to note here, and you'll see our second window is in the next step. It's important to note here that our second window starts at 10. This is because we set a step size of 10, meaning that this is the overlap we're creating. Next, we're going to iterate through these groups of windows, extracting the start times, the end times, and the list of 24 values that we saw. And we're going to use these values to create a new data frame with that collected data. So if you take a look here at our new data frame, it goes from 0 to 23, meaning that there's 24 values listed in one row. So let's normalize these sensor windows then.
So that's a really interesting step there that you did, Megan, which is creating a time window that's moving through the time series data. And so that intervals at 10-second intervals, but each time window has 24 points in it, correct?
Yeah, 24 points. And now that our time series has been split into separate windows, we can treat these now as a separate sample each.
Yep, and I'm just going to pull up on the screen. We did have a question in the chat. Mukta had asked, are there any pre-built industry models part of KDB AI, and if so, which are those? So just what we're doing today is using time windows and similarity search to find similar time series data in our data set. KDB AI doesn't ship with any models, but we do have some sample demos on the KDB.ai Learning Hub, where you can find how you can search legal documents or search market data or search image scan data like MRIs. So you can use different models as you'd like with this vector database, but the vector database itself doesn't ship any models with it. And just wanted to point out for everyone else while I'm taking this pause here that if you have any questions, feel free to put them in the chat. And if you're having trouble with the live stream on LinkedIn, sometimes the LinkedIn live stream can like reset itself. Recommend you hop over to our YouTube channel. We are also streaming there, and that tends to be a lot smoother. Okay, sorry for interrupting, Megan. I'll let you get back.
No, so now we're just going to move on to normalizing the sensor value windows. So here we're just defining a function called normalize vector. And if we run that, you'll be able to see now our values are oscillating between 0 and 1. So now these values are ready to be stored in KDB AI. So to do this, first you need to connect to your KDB AI session. And for this, you'll just need your endpoint and your API key, which Neil talked about at the start of the session. They're found on the KDB AI cloud on your cloud account. So once you run the cell, you'll be prompted to enter both them all in there. And then when you run this, you'll then be connected to your KDB AI database. So let's define our table schema then. So this is where we're going to choose what index and metric we're going to use. So we want to add two columns, start time and end time, which capture the beginning and the end of those windows. Here we're also going to define our vector column. So when defining our index, we want to use dimensionality, which is the same as our window size, which we're doing here. Next, we're going to define our metric, our similarity metric, and here we're choosing to use L2, or Euclidean distance. And finally, we want to define our index type. Here we've decided to use HNSW. Now, if you want to know more about similarity metrics and index types, we have that all in our Learning Hub on KDB AI.
Yeah, I just wanted to mention there. So just to reiterate, the dimensions is the window size. So you have 24 dimensions in your window size. You have 24 data points in your window. So these vectors are 24 elements long. And then Euclidean distance is going to find nearest neighbors based off of distance and vector space, how near or far embeddings are to each other. And then HNSW is hierarchical navigable small worlds, a little bit of a mouthful, but that is a graph type index that is often very quick to perform and has good accuracy. So it's usually what I start with when I'm trying out a vector search, a similarity search. It's a great place to start. But if you wanted to learn more about the different types of index methods and the different type of distance metrics, there are articles on the Learning Hub to learn. Thanks. I'll hand it back to you, Megan.
Perfect. Thanks, Neil. Now we're just going to create our vector table. So this first cell here is just going to check that the table does not already exist in our database. And if it is, it's just going to delete it, which it doesn't exist. And then here we're just creating our table using our create table function. We're giving it the name sensors and we're passing it that table schema we just created above.
So it's creating a table called sensors using the sensor schema that you defined and we just discussed.
Now we want to add our embedded data to our KDB AI table that we just created. So to do this, it's always good practice to check the size of your embeddings data. Since if it's too large or usually over 10 megabytes, then you'd prefer to chunk it, insert it into your table by chunking. We've just checked the size of our data there now, and it's around 4 megabytes, so that should be fine just to add all in one chunk. So here we've just inserted our data, and then we can check to see if it's been saved by querying our table. And you can see here that that's worked fine.
So that's really, so if we can hover on that for a second, those results. So what we're seeing is each of these windows that start and end time of the window, it's just kind of metadata around the vector embedding itself. But then we're seeing the vectors and those embeddings. So we're taking those numbers that were the water pump machine data readings, the pump readings, and we are translating that and embedding that into a vector embedding that is a representation of those numbers that can be better used for similarity search.
Yeah. So now we're going to perform our pattern matching on our historical sensor data. So the first step you want to do when doing this is you want to select a historical pattern that's going to be your query vector. So here you can see that we're just using a random start time of 1 p.m. on the 1st of the 4th, but this can be any time window you choose. Here we're just selecting our historical pattern, and these are just matplotlib functions to allow us to visualize our query pattern before we run our search. So here then, this is our query pattern. So you can see here that we have 24 points, and you can see they oscillate around the 2.45 margin. So this is going to be our query vector then. So now we're going to search KDB based on these results. So
we're going to take that sample of that time series signal, and this is noisy data, so it's going to bounce around a little bit. It's bouncing around 2.455. But then we're going to search the vector database to see what other windows of time are similar to this window that we have right here. And this window is based off of when there is a broken sensor, right? Or a broken equipment, right? The sensor is still operating. Yeah.
So to be able to do this search, we're actually going to use the embedded version of this pattern. And we can do this by using the embedding data frame we just created above. So we can run that search against KDB.ai. So here we're just asking for the five nearest neighbors. And if we run that, you can see here that we get returned our KDB.ai table along with nearest neighbor distance. So let's visualize these results then. So if I run these, so these are just some functions for visualization. And this is our result. Now, as I said before, oh, I might have forgot some. Let me see. So as seen before, our nearest neighbor 1 is our query vector. So we're keeping that in to compare the rest of the results. So you can see here that the blue one then is our query vector, and then the rest is our nearest neighbors. So you can see here that the points sort of match up and the drops they're align in a similar pattern. So you can see here that we've got a really stable period and we've got good results from this.
And that's very fast, right? So if you go up to that chart, like this is our kind of key results. You see, again, the blue line is your query vector. And if you want to go to that chart, Megan, can you go down to that chart just a second?
Yeah.
Yeah. Okay. I think there was a little lag on the stream. Sorry.
Yeah.
We actually have a question about this. So kind of while we're talking about this, Eamon was asking when we have the 5 nearest neighbors and an approximate match. So do you have any bounds or guarantees on the return matches? So you can actually set your distance measure, and you can do this in some post filtering. You can return the Euclidean distance score. So how close of a match or how far of a match those are, and you can filter your results on that. So that's one way that you can bound it. So just taking a simple query vector, searching across 6 months of data, and we're finding super similar time series windows to that query vector in a fraction of a second.
Yeah, I also meant to mention with this table that you can see here, the top one has the nearest neighbor's distance of 0. We actually chose a start time, which was a query pattern. So obviously it's going to give a nearest neighbor distance of 0. Now you can remove this if you don't want to see it, but I meant to say we're going to keep it in as it's useful for visualization in the next section. And here you can see it now that you can compare. Yeah. So this is our original one. You can compare your nearest neighbors to it, which is good for visualization. So now, so you can see there that we got really good results. So we're just going to run another query vector just to back this up. So this is all in the one cell, so it's easily rerun. And if you run this, we're just changing, the only thing changed about this is the start time. Everything else is exactly the same or near enough the same. So here we're just choosing a start time at 10 past 9 and then on the 12th instead of the 1st. So here again, you can see that we get really similar results. The points go up at the same, near enough the same time. The drops go off the same time. So we got really good results from this, as similar to the last one. And just to finish off then, so there's actually a really useful feature that we have, which is filtering. Sorry, did you want to say something there, Neil?
Yeah, sorry, I was just gonna, I didn't mean to interrupt again, but we had a bad connection for a couple seconds.
Okay.
Can you re-explain what you meant about the start time? You changed the start time just to find a new query vector, is that correct?
Yeah, it was just another example of a query vector. Just it was only the start time that had changed. Everything else is relatively the same. We've just changed here the start time to 10 past 9, and we've changed the date to the 12th instead of the 1st. So every time it's just another example, just to show another example of a different query vector, just to show that we've got similar
Great.
results. And just one last thing I want to show before I end. So we can also do things like filtering the results on additional columns that we've added. So here I'm just going to add, so we've got the nearest neighbor is 5, and here I'm just going to do some filtering. So if I just include this. I should have just copied and pasted this. Let me see. So here, if we just run this again, you can see here that now we've filtered, and it won't show anything from, we're only filtering on August onwards, so you won't see anything from April. So there's just the option you can filter your metadata as well.
That's just another way to bound your search, as Eamon was asking about. So that's great. Great point.
But that's all from me, Neil. I'm gonna hand it back
All
to you.
right, great. Well, thank you so much for showing that, Megan. I think that this is really exciting in the fields of temporal analysis. I wanted to let the audience know that next week we are going to get into a hot topic of retrieval augmented generation, or RAG, using LangChain with KDB AI. Now, this is just going to be a naive RAG, general RAG introduction, kind of a soft introduction to what it is essentially enriching your LLM, your large language model, with the knowledge base. So you're able to do some similarity searches with your vector database, like Michaela did on our first session, where she did a document search and she found similar snippets of or chunks of text data for her search. But then you're actually passing that to a large language model like GPT-4, GPT 3.5, and you're able to actually have a conversation with your data and have the LLM take those chunks and create a nice contextualized response for you. So what that allows you to do is extend the capabilities of your LLM, use your company's data, use your private data, use real-time data, use your own personal data with the vector database to have a conversational chatbot. It's a very hot topic again. So we will have Ryan showing that with us. And then I wanted to let you know that we have the LangChain RAG session next Wednesday, same time. Then we'll do a sentiment analysis one same type of workshop where we're going to go through a notebook, and then we're going to talk about approaches to RAG on a second Wednesday of November. And this will just be kind of an overview of different retrieval augmentation approaches. And there's a lot of different approaches to RAG out there. And so we wanted to kind of get those all aggregated together and share those to you as a nice summary. So with that, I want to thank you all for joining today, and thank you, Megan, for your time and that excellent demonstration. Our audience should be sure to sign up for kdb.ai at kdb.ai in your browser, and let us know in the chat if there's any other sessions that you want to see in the future. But with that, we will leave you, and thank you again for joining. Thanks, Megan.
Thanks, everyone. Thank you.
Bye.